This is problem 60. A beam of protons is injected into the velocity selector at right. The magnetic field is 20 milliteslas directed out of the page. Now we should go back to problem 59, which is a homework problem, to see what a velocity selector is. So the top of page 59 reads, the device at right is a velocity selector. By adjusting the uniform electric and magnetic fields in the region between the plates, only particles of a specific velocity will exit the device through the hole in the second plate. That hole is here. So particles with a specific velocity will go straight through and exit, and particles with different velocities will not exit, so it selects particles with a certain velocity because only particles with that velocity will make it through the hole at the other side. The electric field is directed downward, and the magnetic field is directed into the page. Now, that's slightly different than what we have here. We have the magnetic field directed out of the page, and we need to figure out the magnitude and the direction of the electric field, which is necessary to select protons at point 6C. So, we need to figure out the forces that are acting on the proton, and we're going to ignore the force of gravity. If you want to calculate it, you will see that it's very small compared to the electric force and the magnetic force. So we have a magnetic force acting on the proton, and the particle is going this way. So there's my velocity vector in red so we don't confuse it with the force vectors. So if the particle is going this way and the magnetic field is coming out of the page, then the magnetic force is going downwards. So I have a magnetic force going downward, the directions given by the right-hand rule. And so if the particle is going to go straight through, it can't accelerate in the vertical direction. And so we must have the electric force pointing upward to balance out the magnetic force, which is going downwards. And we could actually write both of those forces using the Lorentz force law, which includes both the electric force and the magnetic force, which is acting on the particle. So the net force is equal to the charge times the electric field plus the charge times V crossed with B, and that is the Lorentz force law. Okay, so I figured out the direction that the electric force must go in. Because these are protons, the field and the force point in the same direction because the electric force is equal to Q times the electric field. So I figured out the direction, and now I need to figure out the magnitude of the electric field. Well, my diagram up here shows me that these forces must be balanced, so they have to point in the opposite direction so that the particle doesn't accelerate up or down, otherwise it would not make it through the hole. So the net force here needs to be equal to 0, so you could say, actually look at this, if the net force is equal to 0, it doesn't even matter what the charge is because you could divide both sides by the charge, which is not 0, so it's okay to divide by it. So what's left in parentheses must be equal to 0. So you could say the forces are balanced, so Q times the magnitude of E is equal to Q times the magnitude of V crossed with B, but the charge would cancel out. So that came from saying the magnitude of the electric field has to equal to the magnitude of the electric force has to equal the magnitude of the magnetic force. Okay, so I can find the magnitude of the electric field by taking the cross product here, but the velocity is perpendicular to the magnetic field And I really only need the magnitude, so that would be the magnitude of the cross product here would be the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between the two, but the angle between the two is 90 degrees. So I can just say magnitude of the electric field is equal to velocity times B. I know the magnetic field is 20 milliteslas, and I want the velocity of the particles that exit to be 0.6 c. So I have the velocity, which is 0.6 times c. You can look this up on the back page of the textbook. Well, it's supposed to be the back cover. For you, it might not be on the back cover. If you bought the textbook from the bookstore, it might be the last page in the textbook. Or you can go to the Spiral Physics folder on the M drive, which is in the Physics 261 folder, and there's a PDF file there called something like back cover. And there, I think it says the speed of light is 3 times 10 to the 8th, but we can use more significant figures. You don't have to, but I like to. And say 2.998 times 10 to the 8th meters per second, and we put that in for C. And then we have 20 milliteslas, and you can convert that to teslas. I'm not going to show the work for that. I'm just going to say that this is equal to 3.598 times 10 to the 6th. And the units for the electric field are supposed to be newtons per coulomb, and I guess we'll show this. So a Tesla is equal to a kilogram per second squared times an amp. So if you take Teslas and multiply them by meters per second, so Teslas times meters per second would be equal to kilograms per second squared times amps times meters per second. So now we have kilograms times meters divided by amps per second cubed. I need a Newton, which is a kilogram times a meter per second squared. So the kilogram times the meter times divided by the second squared, that's a Newton. And what is an amp times a second? That is a coulomb. So this is equal to newtons per coulomb, and we can breathe a sigh of relief because it works out. But you don't have to show me that in homework. It doesn't hurt to check, because if it doesn't work out, then probably you did something wrong, and you might use that to go figure out where your mistake is. Or you can just trust that it works out and stick in the units at the end. So we have 3.598 times 10 to the 6th. You can round that to 3.6 times 10 to the 6th newtons per coulomb. That is the magnitude, but they asked us for the magnitude and the direction, so let's just write this now as a vector, and the magnitude, let's round it to 3.60 times 10 to the 6th. This is newtons per coulomb. And we said the force is going upward, so that would be the j-hat direction, and the field and the force are in the same direction, so the field is in the j-hat direction, and there is my answer for part A. For part B, I want to know, where do the higher velocity protons strike the second plate, above the hole or below the hole? Well, the velocity does not affect the electric field. And because it does not affect the electric field, it does not affect the electric force either. So the electric force stays the same, but the magnetic force is equal to QV crossed with B, and this is dependent on the velocity. If the velocity increases, the magnetic force is going to increase also. So the magnetic force increases. The magnetic force was pointing downward. So let's just draw a little picture here. Now the magnetic force is larger than the electric force. So if the force that's pointing downwards is larger, the particles are going to strike below the hole. And in part C, if the beam is replaced with a beam of electrons traveling at the same speed, do the electrons pass through the hole, do they strike the plate above the hole, or do they strike the plate below the hole? Well, the charge is different, but in fact, the charge canceled out when we did this, when we set the magnitude of the two forces equal to each other. So when you look at the electron, because it's negative, the direction of each force changes. But the value of the charge didn't matter when we solved this. So we have now the electric force pointing downwards. We have, it's supposed to be the same size, the magnetic force pointing upwards. But it's still true that the magnitude of the electric field is equal to V times B. And the electric field is what it is. It doesn't depend on whether it's an electron or a proton. The magnetic field is still 20 milliteslas. So if the electrons are traveling at the same speed, then nothing changes here. So electrons traveling at the same speed would pass straight through, just like the protons did. So they would pass through. Okay, so if you calculate the magnetic force and the electric force using Q times E and Q times V crossed with B, the direction changes, but the magnitude of the forces does not change. So the forces are still balanced and the electron passes through.